Welcome to Easy Math TV. We're going to continue our statistics video series with a video concerning developing a confidence interval for a population mean. So this is part of inferential statistics, and it has to do with making an estimate or trying to make an inference about what the true population mean is if we don't know what it is. Okay. So all we have is data or a sample, and from that sample, what can we do? What are we allowed to do in order to estimate what the true population mean is? And obviously, we're not going to be able to get the exact number, so that's why we call it a confidence interval. We call it a confidence interval because the level of confidence will tell us how we can measure the width of that interval. So the width of that interval is going to be affected or impacted by the the level of confidence that we want to have. But it also is going to be impacted by our sample size. You know, there's a lot of players here that are going to affect how close we can get with our estimate of the true mean. And so it all comes down to what we start with, what our sample is. So this method that we're going to talk about today involves a couple of things that we have to assume. So there's some things that we need to be able to state about the population in order to use this method. And one of them is that we need to be able to know what the population standard deviation is, sigma. So that you can see here in row 8. So that number is a number that we would actually be typing in. And then the confidence level is also something that we would be starting with, but we can determine that ourselves. We also absolutely need to know what our sample size was, and the sample size needed to be 31 or more. And in this case, our data, the data is over here in column A, and the data actually is a sample of size 31. So we met that requirement. And we also need to sort of be fairly certain that these x's here are the data is our x's, that the x's come from a normal population. So the x's have to be normally distributed, and we can see from our histogram here. I mean, it's a little bit crude, but we can be fairly certain that these x's come from a normal population. Okay, so those have to be the case. And normally I wouldn't even go over this method. Like, I would just use the second method that I'm going to be showing you. But some textbooks actually require that you do this, so we're gonna do this just so that you can be familiar with the technique. Okay. I'm also going to point out two things here, that the sample variance and the sample standard deviation we're not going to be using those pieces of information, so I'm not even going to discuss those. Those were just numbers that I just happened to calculate because I was curious about them. All right. So the sample variance and sample standard deviation are not needed, so we're not even going to use them. All right, so as we go, I will explain everything that you're seeing here. And let's start with the calculations here in columns C and D. All right. So basically, column D, as in David, is going to be where all of our calculations are. So for the sample mean, you're either going to be given that in the problem, or you have your data in front of you. So let's just calculate the sample mean from our data. That's going to be equals average, parenthesis, and then the data sits within these cells A3 all the way down to A62 potentially. It doesn't have to go all the way down to A62, but we have that possibility. So equals average, parenthesis, A3 colon A62. That's going to capture all of our data and calculate the sample mean. That's our X bar. So that's the first of three values that we need to construct our confidence interval. Then we need our sample size. We're going to need that in order to calculate something called the standard error of the mean. So let's start with the sample size. Again, you're either going to be given that in the problem, so just type that into cell D6, or in this case, we're going to just calculate it from our data. It's equals count, parenthesis, A3 colon A62. So anytime you hear me refer to A3 colon A62, that's where my data is. The formula itself is giving us the sample size. So the sample size is equals count, parenthesis, A3 colon A62, close parenthesis. Then, because of the central limit theorem, in cell D7, we need to take the square root of n, and that's equals SQRT, parenthesis, D6, close parenthesis. In cell D8, there's my population standard deviation. I just typed that in, 2.85. And my confidence level is going to be 95% by default. Otherwise, it's given to you in the problem. And that is the probability that the true population mean is within your upper limit and lower limit that we're about to calculate. So the confidence level is the probability that our sample contains the true mean. All right? That's basically what it is. So it's just a probability of us being correct in our assessment of what the confidence level is. Next, we need the cumulative probability. So this is the confidence level plus the left tail, because the confidence level is basically centered at the mean, and it goes to the left and to the right. So there's a tail on both sides of our confidence interval. So in order to find our z value, which we're about to get, we need that. In order to get that, we need the cumulative probability. So that's going to be our confidence level plus the amount that's in the tail. So this is how you calculate that. In cell D10, you will type equals, and it's D9 plus 0.5 times, parenthesis, 1 minus D9, close parenthesis. So basically, whatever's missed by your confidence level, that's the 5%, we need to take half of that and add that to our confidence level, and that gives us our cumulative probability. So again, that's equals D9 plus 0.5 times, parenthesis, 1 minus D9, close parenthesis. That's our cumulative probability, 97.5%. The standard error of the mean is sigma divided by the square root of n. So that's going to be equals D8 divided by D7, and that's located in cell D11. Again, that's equals D8 divided by D7. Sigma divided by the square root of n. And that's our standard error of the mean. So that's the second number that we're going to need in our lower limit and upper limit calculation. The third number is the z-score for our cumulative probability, and that's in cell D12. So in cell D12, type equals norm.s.inv, parenthesis D10, close parenthesis. So remember, D10 had the cumulative probability in it, and we need the z-score of that. In a previous video, I explained to you how we get z-scores using Excel functions, and that is the equals norm.s.inv function, parenthesis D10, close parenthesis. So if you were to picture this on a number line, at the center of the number line, we would have our X bar, which is 64.74. And towards the left side, we would have something called a lower limit, which is going to be X bar minus Z times our standard error of the mean. And then on the right side, you would have a number that we're about to calculate. It's going to be X bar plus Z times the standard error of the mean. So in a minute, we will know what those two numbers are, and you can actually picture them on a number line if you wanted to. And we're basically going to be 95% of the time when we take a sample of size 31 from this population, 95% of the time we will capture what the true mean of the population is within our confidence interval. Okay? So let's calculate the lower limit and upper limit into our cells G9 and G10. So in G9, we're going to type equals D3 minus D12 times D11. And again, the reason for that is because that's our X bar minus Z times standard error of the mean. Okay? So that's where those numbers are located. Equals D3 minus D12 times D11. That's our lower limit. And then the upper limit is in cell G10, and that's equals D3 plus D12 times D11. Again, equals D3 plus D12 times D11. So I want you to imagine now on our number line, right at the center would be 64.74. And to the left of that, somewhat to the left of that, is going to be 63.73. And then over to the right, that's going to be 65.75, because that number we want to round up. So I'm just going to type in here, the lower limit we want to round down, the upper limit we want to round up. And that's because of our confidence interval. We want to make sure that we capture the true mean inside of these numbers. So you'll notice it's an open interval, okay? So the statement we would make here is the 95% confidence interval for mu, not for X bar, for mu, is parenthesis 63.73 comma 65.75 close parenthesis. So that's if we were to express it as an interval, which can also be written as, so we could also write it as a double inequality. Sometimes you see it written like that in some textbooks, with mu at the center of the double inequality, and it would be written 63.73 less than mu less than 65.75. So that just means that mu is in between those two numbers. So would it be considered statistically rare if we had a sample from this population where the sample mean was 65.7? And the answer is no, because that value is within the 95% confidence interval. I mean, it may be all the way to the right, but it is within the 95% confidence interval, so it is not considered to be statistically rare. If we wanted to make the confidence level so that we didn't have a total of 5, if we didn't have like 2.5% on each tail, suppose we want 5% on each tail, then we would have a 90% confidence interval. If it's a 90% confidence interval, we can actually shrink the interval slightly. So instead of starting at 63.73, it would start at 63 point, well, actually that 63.9, right? I mean, or you could just say 63.89. 63.89 would be on the left, and because we're rounding down, right? And on the right, it would be, the upper limit would be 65.58. So if we had a confidence level of 90%, we could shrink the interval slightly. If our confidence level was 99%, so we wanted to be, if we wanted to be even more certain, then we have to widen the interval. The interval is going to be bigger. So the lower limit then would be 63.42, and the upper limit would be 66.0. Well, we could just say 0.06 because there's a 0 after it. 66.06, you know. So, yeah. So if you want a smaller interval, you have to decrease your confidence level. Decrease the confidence level if you want a smaller interval. So, 95% is pretty good because that distributes the tails evenly on both sides. 2.5% of your values would be on both sides. And, so that covers you with the fact that we have kind of our sample size is kind of on the small side anyway. So we probably wouldn't want to lower our confidence level anymore. Anyway, that is a confidence level for the true population mean, given a sample statistic and knowing what the population standard deviation is. Like, subscribe, comment down below, share these videos with people if you think they will find them useful. And in our next video, we'll talk about a confidence level for the mean when you do not know what the population standard deviation is. So I'll see you in the next video.